So here's another example, a little bit more complicated than the last. The function here is x cubed plus 2x, and we want to find the derivative. We're going to use the definition of the derivative. I'm going to use the x plus h form. Alright, so I'm taking the limit as h approaches 0. This part right here is our f of x plus h. Okay, and to get f of x plus h, all we're really doing, at least mechanically, is every time I see an x, I'm going to replace it with a set of parentheses and an x plus h. So here I have x cubed, now it becomes, in parentheses, x plus h cubed. Plus a 2x, f of x plus h is going to be 2 times parentheses x plus h. And then I subtract f of x itself, just x cubed plus 2x, and that's all over h. Alright, so if you don't remember Pascal's triangle or the pattern that this cubing a binomial has, this can be some work. But I promise once you do it once, you'll remember it. The coefficients, so that x plus h cubed is this term right here, or those 4 terms. So just think that the coefficients are 1, 3, 3, 1. The first term in that binomial goes cubed squared to the first power, nothing there. The second term in the binomial, there isn't one in the first term, but then it goes h squared, h cubed. Alright, so that's the pattern when we expand a binomial, when we cube a binomial. And then here I just distribute the 2 to the x and the h. I get 2x plus 2h, and then I distribute this negative sign, minus x cubed minus 2x. So we've done the hard work now. Lots of those terms cancel out. I have, let's see, x cubed minus x cubed. I have plus 2x plus 2x, plus 2x minus 2x cancel out. So I have 3x squared h, 3x h squared, h cubed, and 2h. All of which I can factor an h out of. Once I do that, I can cancel the h in the denominator. And then what's left, I'm going to substitute an h equals 0 here and here. So all I have left is the 3x squared plus 2. So that's my derivative there, the 3x squared plus 2. Alright, there's also an alternative form of the derivative that we can use, and it looks like this. So this form of the derivative, we usually use this if we're looking for the derivative just in a single place. So you see that we just get the derivative at this value of c. Now we're not dealing with h approaching 0, we're dealing with x approaching c. So we still are we have a difference quotient here, and we're dealing with the stationary point. And then we have another more general point here that we're bringing closer and closer and closer to the original point here, c f of c. We use this because it usually produces an easier limit. Both c and f of c are just numbers, right? It's just the x value and the y value that goes with that x value. And so usually this is an easier limit. The drawback is that we just get the derivative, or the value of the derivative, at that c value. So if we want it in multiple places, we would have to do this over and over, whereas once we get this derivative, you can just tell me which x value you want me to find the derivative at, and I can plug it in there and get it quite easily from there. Right? So there's pros and cons here, but especially with complicated functions, this is a nice one to use if we just want the derivative in a single place. So here's an example. If I want to find the derivative of x to the 4th plus 3x cubed minus 5x plus 1 at x equals 1. Alright, we can see that this is just a polynomial, so it's not that we can't do it using the x plus h notation, but it would be a lot of work if we had to do a x plus h to the 4th power plus 3 and then an x plus h to the 3rd power and so on. You can see expanding those would be quite a bit of work there. Right? So instead I'm going to use this alternative form. And so I'm going to use just f of x, and then I'm going to evaluate the function at, in this case our c value is -1, and then I'm going to have x minus -1. All right, so I have, here's my f of x. I evaluate my function, my original function here, at x equals -1. So I have 1 minus 3 plus 5 plus 1. I get a 4 there. So I have f of x minus f of c, and then x minus c. And all that, we're going to take the limit as x approaches -1. Okay, so I end up with x to the 4th plus 3x cubed minus 5x minus 3 all over x plus 1. And this looks like a factor and cancel kind of problem. The problem that I have, or the challenge that I have here, is that this quadratic is not easily factorable. All right, so I need to think a little bit about how I'm going to deal with that, and we're going to have a little bit of a throwback to your probably an Algebra 2 class, and we're going to talk about how to deal with this. I know that what I want to do with this quadratic is factor it so that it's something times an x plus 1 term. That way I can cancel out the x plus 1 term. Right? So we're going to kind of go back and review a little bit about how to do polynomial long division. So the way I'm going to set this up is I'm going to set up all my powers of x. So I have an x to the 4th. I have an x cubed. I do not have an x squared here, so I'm going to use 0x squared just as a placeholder. And then minus 5x plus 1. All of that, I'm going to divide out the x plus 1. Alright, so watch the way I do this. When I do the polynomial long division, I only care about the leading terms. So I do x to the 4th divided by x gives me an x cubed. Now I'm going to multiply that x cubed times the x plus 1 and write it down underneath this polynomial. So x cubed times x is going to give me x to the 4th. Because we divided the leading terms, when we multiply this back down, the leading term should always be the same one as we had above. So x cubed times x is x to the 4th. X cubed times 1 is x cubed. Now we're going to subtract down. Alright, so I have x to the 4th minus x to the 4th. 3x cubed gives me minus x cubed gives me 2x cubed. And then I'm going to copy down the rest here. I'm going to continue that pattern. So I divide the leading terms. 2x cubed divided by x is 2x squared. Then multiply the 2x squared by x plus 1 gives me 2x cubed plus 2x squared. I'm going to subtract again. 2x cubed minus 2x cubed is 0. X squared minus 2x squared is negative 2x squared. And then I copy down the rest. Here, you know what? I apologize. This last term, it hasn't really hurt us yet, but this last term should be a minus 3. My polynomial here was minus 3. So luckily we haven't really had to deal with that yet, but pretty soon it will make a big difference. So again, I divide my leading terms. Negative 2x squared divided by x is negative 2x. The negative 2x times x is negative 2x squared. Negative 2x times 1, negative 2x. Again, I subtract. I got to be careful of these negatives. I have negative 2x squared minus a negative 2x squared is 0. Negative 5x minus a negative 2x is negative 3x. And now, very important that I fix that plus 1 to it, make it a minus 3. Now I have negative 3x divided by x gives us negative 3. Multiply it down again, negative 3x minus 3. So if this process works for us in this situation, we want to get a remainder of 0. All right. So what that means is if I take this fourth degree polynomial and divide out an x plus 1, I'm left with this third degree polynomial. So that means that that numerator can factor in this way. Alright, so I can see that by dividing out that x plus 1. And then of course from there it's an easy problem. I cancel out my x plus 1 factors. Then I just have x cubed plus 2x squared minus 2x minus 3, and I'm finding the limit as x approaches negative 1. So when I make that substitution, I get, let's see, negative 1 plus 2 minus 3, and I get my 0.